I like to record these just in case anybody wants to go back and look at it again. So I'll be doing that, and then I'll post it up on Google Classroom. Okay, so here we have two lines that intersect. If we have two lines that aren't parallel, what's the maximum number of places they can intersect in a flat Cartesian plane? How many places can two lines intersect?
One?
Yes, I'm hearing one, I'm seeing one. Taylor, I saw your finger up first. Why just one?
They're straight lines. They only cross once.
Yes.
It's not like they curve around yet.
Yet, exactly. So this is one of these things where we can start to see where coordinate systems depend a lot on our frame of reference. This is flat. Let's say that we're looking at a globe. Can straight lines intersect in more than one place on a globe?
Yeah, because they go all the way around in a circle.
Yeah. Can parallel lines intersect on a globe?
No.
Well, I would posit to you, next time you're looking at a globe, look at those lines of longitude. Again, longitudinal lines go from pole to pole. And in fact, if we were all right up at the North Pole together, we could just walk in a little circle and each step could be in a different time zone, because all the lines of longitude, which are parallel, come and intersect at the North and South Pole. So it's really important to note that this question of what's parallel or what's not parallel, what's straight versus what's curved, a lot of this depends on localized geometry. And in fact, one of the things that we get from Einstein's theory of relativity is, for example, that gravity is actually a side effect of space-time being curved, and that although it looks like, for example, the Earth's orbit is a circle, because of this curvature of space-time, it's actually a straight line. We're actually traveling an inertial path rather than an accelerating path. It looks like we're changing direction because we're going in a circle, but actually we're just following a straight line within the curved geometry of space-time. So, fortunately, we don't have to do any of that math in chapter 3. We could just assume that this surface is flat and it continues flat forever, and you are correct, Taylor. In such a system, two straight lines will only intersect at one point unless they're parallel. In a totally flat geometry, how many times do two parallel lines intersect?
None.
0.
Yeah, 0. Or infinity if they're right on top of each other. So they either intersect everywhere or nowhere. And all other lines intersect at just one point.
But at that point, aren't they just the same line?
Well, yes and no. You can have two different equations defining effectively the same line. Does that make them the same line, or are they just twins? We get kind of lost in pedantics at that point. But what I would like for you to do is to go ahead and graph y equals 2x minus 3 and y equals negative x plus 9. Go ahead and graph these, and just by looking at their graphs, determine where these two lines intersect. And so graphing the lines is one way that we can determine their intersection. me know when you've got an answer. Yes, Gio.
Wait, did I say the answer?
Yeah, go ahead.
Oh, 4 or 5.
Can I get a confirmation? Does anyone else? I see some people are still working, so we'll wait. So we've got a suggested point of intersection from Geo. I'm gonna look for confirmation. What's one way, if the proposed solution that we've got here is 4, 5, what's a quick way to check it without even, let's say you haven't started doing the graph yet and you're feeling kind of behind. What's a quick way to check whether or not this is actually where the two lines intersect?
Look at it.
Yeah, you can plug them in here and plug them in here and see if both of those statements are true. If they're true, then that one point is a solution to both of those lines, and that has to be where they intersect, because as we've discussed, this is a flat geometry and these lines are only going to intersect in one place. So, Merlin, when we plug in 4, 5 to this equation,
It works.
because we get what is equal to what's equal to what?
5 is equal to 5.
That's right. Because 2 times 4 is 8 minus 3 is 5. We get 5 is equal to 5. That's a true statement. All right, Gino, let's say we plug 4, 5 into this line. What statement do we get? 5 equals 5. Because 9 minus 4 is 5 and 5 is equal to 5. So that's a way that even if we don't graph it, that then when we have a suspected answer, we can plug it in and check it, and we find out that it's a true statement, and indeed, this is the place where the two lines intersect. What are the weaknesses of this methodology? If our goal is to find where two lines intersect, this worked just fine. We graphed the lines, we eyeballed it, we found the intersection point, we plugged it in, it worked. What is the weakness of this methodology?
Takes too long. It takes a lot of space.
It takes too long, it takes up a lot of paper. And do all lines intersect really neatly at integers? No. So it'd be very possible to graph two perfectly fine lines and then they don't intersect at a really convenient point like 4, 5. It could be 4.1 and 4.9. And then this is going to end up wasting a lot of time and a lot of paper. So we need a couple of methodologies in order to be able to solve systems algebraically. So the first one that we're going to look at is the substitution method. And if we have the equations of the lines in this format, this is really easy. Who has either already been working on this assignment or has done something like this in the past and knows what we can do, like how the substitution method works? Yes, Lily?
You would get x by itself for one of the equations and replace y in the other equation with x.
We could do that, although in this particular case,
Y would be easier.
y would be easier, and why would y
Because
be easier?
We know that for both of those, y must equal, be able to work with both of those. And if y for each of them, it's the same y, it's going to be the same point, meaning
Yes.
that both of those equations must work. So we could just say that they should be equal to each other and write 2x minus 3 equals 9x plus 9.
That's exactly right. We've already got y isolated, so we can just take these two x sides of the equation and set them equal to each other. Is that what you were going to say, Cece? Yeah. So here we can just say 2x minus 3 equals negative x plus 9. and now this is an equation that we can just solve. So in this case, Mira, we have a few different places to start with solving this equation, but what's one thing that we could do in order to solve this equation?
You could add 3 to both sides.
That's right. So we can add 3 to both sides, and so we get 2x equals negative x plus 12. What would be a next step that we could do, Jose? We're trying to solve for x, meaning we're trying to get x by itself. So what's something else that we can do here in order to solve this equation? Yeah, we are going to do that step of dividing by the coefficient of the x. But in this case, do we have all of our x's together yet? No. So let's get them together first and then do the division. So what should we do next before we divide? Yeah, we want to move the x, exactly. So we're going to go ahead and add x to both sides. So now we've got 3x equals 12. And now we're going to do that division step. Technically, we could have done that first, but then we were going to end up with fractions, which very few people are thrilled to see. And so 12 divided by 3 is 4. We end up with x equals 4. Am I happy or sad to see x equals 4 at this point? And why?
Happy.
Yeah. Yes, I'm happy. Why am I happy to see x equals 4?
X does equal 4.
Right, because we already have shown that x is equal to 4. So this just nicely shows us that the substitution method works. Okay, I've solved for x. Am I done with this problem? No.
You have to plug 4 in for x.
That's right. So we have to, and does it matter, of our initial equations, does it matter which one I plug 4 into?
No, just pick the easier one.
Yeah, pick the easier one. To me, this one looks easier. So here, I'm going to say y is equal to negative 4 plus 9, and y is equal to 5. Am I happy or sad to see 5? Gino's just like nodding. It's yes, we're getting victory fists from Merlin. We are thrilled. We are the champions. We have algebraically found the point of intersection between these two lines. Now, a lot of these problems, the equations are going to be given to you in standard form, meaning that you are going to get your equations in the form y minus 2x equals negative 3 and y plus x equals 9. So in this case, we had kind of a leg up because we already had y isolated because we had the lines in slope-intercept form. Often, though, in this section, you're going to be given the lines in standard form. In this case, this is where where our first step would be potentially to isolate x in one of these equations, like Lily C suggested. When we're looking at these equations, though, we don't necessarily have to solve for x or to solve for y. We're just looking for the one that is going to be easiest to get alone. And in this particular case, actually, we have a lot of candidates. It's going to be easy to solve for this y. It's going to be easy to solve for this y. It's going to be easy to solve for this x. And then whatever we get, then we can plug it into the other equation. So let me do just one quick example of that. Let's say that we decide to solve for this x. we subtract y from both sides, and now we have x equals minus y plus 9. This we can now substitute into the other equation. So we're going to have y minus 2 times negative y plus 9 equals negative 3. Now we've got some simplification to do. But the key is, whether we're looking at the prior example or we're looking at this example, if we're going to solve one equation, we need to get it down to one variable. So here we've substituted in this minus y plus 9 for this x. All right, and now help me out, folks. This is going to be a little bit difficult to simplify here because we have to be really careful to mind the signs. What do I get when I distribute this minus 2 to everything that's inside the parentheses? Calling on you for this one, Cece.
2y, or y plus 2y times 18 equals negative 3. And then that turns into 3y.
That's right. So we have to be careful to multiply negative 2 by negative y, which gives us a positive 2y, and negative 2 by 9, which gives us a minus 18. And you're correct. Now we have 3y minus 18 equals negative 3. What's our next step here, Cece?
Adding it, and that turns into 15, then it turns into 5.
That's right. So we've got 3y equals 15. Divide by 3, divide by 3. I end up with y equals 5. Am I happy or sad to see y equals 5? Happy, because we know from the work that we've already done that we are expecting y to be 5. Okay. So this is another way that the substitution method can work. So this is the substitution method, and this is two different examples of the substitution method. I'm going to leave space here, a little space, for one other method. This is called the combination, or alternatively, the elimination method. So here our goal is, we're actually going to combine the two equations together. In the substitution method, we substituted one piece of one equation into the other equation. In the combination method, we're actually going to combine the two equations together. But we're going to carefully do it in such a way that we eliminate one of the variables. So that's why this is called both the combination method and the elimination method. We can see, looking at this equation, at this system of equations, that combining these two, negative 2x plus x almost eliminates the x. What would be one adjustment that would mean that when we combined these two together, the x's would totally x each other out? Yes, Cece?
Multiply it by negative 2. Wait, I mean positive 2. Sorry.
Yes. That's right. If we just multiply everything in this equation by 2, which we're allowed to do, as long as we do the same thing to both sides of an equation, we have not interrupted the balance. So we multiply both sides of the equation by 2. Now when we combine them, y plus 2y is 3y. Negative 2x plus 2x cancels out, It is nothing. It's like matter and antimatter. They have annihilated. And negative 3 plus 18 is 15. So we've combined the two equations together in such a way that the x's have disappeared. Now this is looking very familiar at this point. Now we've got y is equal to 5. We're happy to see that. To complete this, we also need the x-coordinate. How do we find the x-coordinate?
Plug 5 in for y.
That's right. We just plug 5 in for y, so I'll go back to this initial equation. 5 minus 2x equals negative 3. Negative 2x equals negative 8. Divide by negative 2. X is equal to 4. These numbers are becoming very familiar at this point. But this is helpful because we can see whether we're doing the graph and then checking the apparent point of intersection, or we are doing the substitution method, or we are doing the combination method. In all cases, we're just finding the single point where the two lines intersect. And this is what chapter 3 is all about. And although it looks very different, this is actually what chapter 4 is all about. So this week we are dedicating ourselves to the pursuit of finding the intersection between lines. Does anybody have any questions about anything that is up on the board right now? All right, well in that case,